Hello, good afternoon, learners. This is Monica Jain from Sri Lanka College of Engineering. Today we are at the fourth lecture of structural engineering, and today we will try to learn about the concept of pre-stressing or the pre-stressed concrete. Now, now your pre-stressed concrete is different from your conventional concrete due to the application of an initial load on the structure prior to its use. The initial load or your pre-stress is applied to enable the structure to counteract the stresses arising during its service period. In case of reinforced concrete, we have seen on day before yesterday that deflection has another impact. In reinforced concrete, which is made up of steel, which is much more elastic than concrete itself. In order to mobilize the strength of your steel, first it has to scratch a little bit, but unlike steel, concrete is very much brittle. So it will not scratch. So when there is demonstration or when we will try to make testing on RCC, in that case, if it is your under reinforced, then your failure will be your ductile failure, and if it is your brittle or your over reinforced section, then your failure will be a sudden failure or the brittle failure. When we are dealing with RCC, when we have to design our reinforced cement concrete structure, so deflection is there. So too much of deflection can be considered into the service line. But those cracks are not look bad, but in actual structure they could allow water and contamination to come into contact with the reinforcement. Eventually what will happen? This will corrode or weaken your reinforcement. So this is what the drawback of your RCC. Again, when we are dealing with the running loads or the moving loads, in that case, or if there is a traction, there is sudden increase or decrease in the load pattern. In that case, there are chances of the fatigue, or there may be chances of change in the stress pattern of the load configuration. So one of the solution to this problem of deflection in concrete member is your pre-stressing. Or in pre-stressing, what we do, we put compressive stress into the structural member before it's put into your service line. This is normally accomplished by tensioning the reinforcement within the concrete, and this gives the member a compressive stress that will balance your tensile stresses imposed to the member once it will put into the service. When we are talking for the conventional reinforced concrete, it doesn't have any compression when it is to be kept into the service line. So it will deflect too much well before it's time for the danger, or not being in a strong enough condition to hold the enough load. So with the conventional concrete, what is happening, we don't even get full advantage of the structural strength of the member. But when you are dealing with your pre-stress, or when you deal with the pre-stress reinforcement within the concrete, we do not necessarily increase its strength, but we have to reduce its deflection. And how this deflection will be reduced? By introducing the compressive force into the member prior to its servicing life. This balances out your maximum load, which allowed under each of the structural design criteria, and also allowing us to take full advantage of the strength of each material, that is your concrete as well as your steel. Here you can see, when we will apply load, there will be deflection if it's a reinforced cement concrete member. But when you are applying load or you are giving stress to the tendons. So what is happening? You are applying compressive load to the concrete member prior to its service life, and that compression will be released when an external load or impact load will be coming out on the member. So this method or this philosophy was first of all introduced by President in 1904. Here we can see when the typical external load will come on the RCC concrete beam or RCC element, there will be crack formation, or again there will be deflection. So the serviceability of the RCC member will totally depends on the deflection and the crack patterns. Wherein when we are dealing with the pre-stress concrete, if your member will get deflect, if your member will get deflect beyond certain limits, so what will happen? There will be uncertainty that whether we should use it or not. There will not be a complete failure, but a deflected member will looks like it is not at all serviceable when we have to use it. But when we are talking for the pre-stress member, what is happening? Your structure is going to get compressed, or you are giving a tensile force into the tendons before its prior use. So what is happening, as there is tension into the concrete ends as well as into the tendons of your member. So once your member is kept into the service, then after applying the external loads, that tension will release with the compressive force of the concrete when external load will going to apply it, and it will nullify the deflection as well as the cracking into your pre-stressing members when it will be in full service condition, or when you will apply the full service loads. So the concept of pre-stressing was invented years ago, and you might have seen the spokes into the cycle wheel. Again, there is a concept of pre-stressing. Then there is a barrel or the wooden barrel. The metal bands induce a state of initial hook compression to counteract the hook tension caused by filling the liquid into your barrel. Then again, pre-tensioning in the spokes of the bicycle wheel. The pre-tension of a spoke in a bicycle wheel is applied to such an extent that there will be always a residual tension into the spoke. So we need an extra amount of tension that will counteract your extra amount of compression when it will come into the existence, or when it will be in the full service condition. The very first early attempt of pre-stressing was done by just stretching the mild steel rod prior to the concreting. Now, when mild steel rods are stretched and concrete is poured into them, so after hardening of concrete, what will happen? The tension in the rod is released, and the rod will try to regain its original size and shape, or its original length, because we have stretched it, but it is prevented by the surrounding concrete. Is it? Again, because there is a bond between concrete as well as steel. Thus, concrete is in state of pre-compression. So now it will not compress again. So what is happening here? Concrete is in the state of pre-compression, and we had applied tension to the tendons. So both are in the extreme condition. So when we will apply external load, it will be capable of counteracting your tensile stresses, such as rising from the load. So basically there are two types of forces when we are talking for pre-stressing. That is your internal pre-stressing force and the external force. Internal pre-stressing force is nothing but your force which will which will apply to the tendons for giving the tension, and external force is nothing but your external force, that is your dead load, live load, impact load, etc. So there are few commonly used terms when we are dealing with pre-stressing. First one is your wires. Wires are nothing but, let me show you a figure. Yes, just observe this figure. Now, wire is nothing but a single unit made up of steel. Here you can see these are your strands. In this strands you may see that there are 7 wires. Okay, so each wire is made up of your either mild steel or HYSD steel. Okay, high yield steel. So this wire is your, this is termed as single unit of this strand is termed as your wire. Then there is a strand. This single unit is termed as your strand, which is composed of your 2, 3 or 7 numbers of pre-stressing wires. Okay, so this is your one strand which is composed of either 2, 3 or 7 number of strands. Then there is a tendon, and tendon is a group of either strands or a wires. Okay, so this will be termed as your single tendon. Here in this figure you may just look here, this is your single tendon. This will be termed as a single tendon, which is a combination of strand, and again in strand there is a combination of, there will be a number of wires. Okay, then there is a cables are nothing but number of tendons. So this total will comprise your cable. Then there are bars. Then bars are nothing but a tendon can be made up of single steel bar also. Okay, so this single wire, strand wire is your steel wire. Then this is your single strand. Then group of strand or wire is nothing but your tendon, and group of tendon is nothing but your a single cable. Okay, so here you can see how many cables are there. 1, 2, 3, 4, 5, 6. 6 cables are there. Okay, how many strands are there? Whatever are the number of strand into this group is your, sorry, how many tendons are there? Whatever are the number of strands into this group will be termed as a single tendon. Okay, this will be considered as a single tendon. Then this single strand is comprises of your single bar or single wire. Okay, so wire is nothing but a single unit made up of steel. Strands are nothing but 2, 3 or 7 wires, and tendons are again group of strands, and cables is nothing but group of tendons. Here in this figure, just look here. Here, this is your total one cable. Okay, the number of strands are, this is one strand. Okay, so these all are the strands. Then number of wires, whatever are the number of units into this strand will be termed as a wire. Then how your pre-stressing works. Now there are two more definitions before going into the principle of pre-stressing on how your concrete and steel interface is there. That is how your concrete and steel are connected. Either they are bonded or not. So the nature of interface is classified as bonded tendon and unbonded tendons. Bonded tendons are when there is adequate bond between your pre-stressing tendon and concrete, then it will be termed as a bonded tendon. Pre-tension and grouted post-tension tendons are your bonded tendons. When there is a perfect bond between concrete and steel or the reinforcement of the tendons, then it may be termed as a bonded tendon. And when there is no bond between pre-stressing tendons and the concrete, then it is termed as a unbonded tendons. Now, when we are talking loading condition, so there are basically three loading condition, three stages of loading. So first stage of loading is termed as an initial loading, or there is an intermediate loading, and final step is a final loading. So initial stage of loading is your during the time of tensioning of steel. Okay, when we are tensioning the steel, that is your initial loading stage. Then when that member will be kept into the service, or when that member will be kept into the practical site, okay, so that will be termed as a in service. So there will be transfer of the pre-stress. Okay, so at initial stage, first your stage of loading is during the tensioning of steel, and second is at the transfer of pre-stress to the concrete. Means when you are stretching that member, when you are stretching that tendon, that stress will be transferred to your concrete. Okay. Second stage is your intermediate stage of loading. So in intermediate stage, it is it includes a load during the transportation of your pre-stress member. Okay, it's supposed to be it is in situ members. There are slippers, there are bridge girders which are in situ. In metro, you are seeing the girders are to be transported from somewhere else, is it? And they are implemented or they are fixed over here. So that is the intermediate stage when your load or when your member is transported from somewhere else. And a final stage of loading is again divided into two stages. At service, that is when it is in operation, and at the time of its ultimate events, or at the time of its extreme events. Okay, so three stages of loadings are there. Initial staging is when you are tensioning the steel. It means you are transferring the pre-stress, a tensioning force, a pre-stressing force to your concrete member. Intermediate stage of load of transfer, that is, it will be applicable when you are applying your load, or it is applicable when you are transferring your load or transferring your member to the side. And third one is your final stage of loading. It will be applicable when your member is in service or during the extreme conditions. Okay. Now see, when we just consider a simple beam, a cross section of a beam. Okay, so what will happen? There will be a direct stress because of the pre-stressing. So that stress will be on nothing but a load by area. Okay, okay, okay. We will cover these two slides quite later. Before that, we will just move to the methods of pre-stress. Okay, so methods of pre-stress. There are two basic methods for your pre-stress. That is pre-tensioning and post-tensioning. So what is pre-tensioning and what is post-tensioning? These are your post-tension cables. Okay. In pre-tensioning system, your high strength steel tendons are pulled between two abutments, or you may also call it as two heads, prior to the casting of concrete. Okay, here in this figure you can see that there are two end abutments, and your tendons, your steel tendons will be pulled between these two abutments. Okay, and the abutments are fixed at the end of the pre-stressing bed, and in between there are number of members. Once the concrete attains the desired strength for Pre-stressing, the tendons are cut and loose from the abutment. In pre, now name itself is suggesting pre-tensioning. In pre-tensioning, your tensioning is done before the hardening of concrete. Okay, when your concrete is in wet condition, at that time only we are going to give the stretching or the tensioning to the tendons in the pre-stressed concrete. Whereas in post-tensioning, we will tension our concrete after the hardening of concrete. Okay, so pre-tensioning name itself is suggesting that we will stretch our tendons before it will get hardened. That is why it is the pre-tensioned member. We will give compressive force to the member before it will get hardened or before it will in the complete plastic stage. Now the pre-stress is transferred to the concrete from the tendon. Okay, here you will apply your jacking force or the pre-stressing force, and those forces will be applicable to the will be transferred to concrete in these members by the means of these tendons. Okay, so once the member will get hardened, we will cut out the extra tendon. So the bond between, because of the bond between them, during the transfer of pre-stress, the member undergoes the elastic shortening. Is it? When you will cut your members from these end, what will happen? The wires or the strands will try to pull themselves away from the tendon and they will try to shrink. So it is nothing but an elastic shortening. If the tendons are located eccentrically, okay, if the tendons are located eccentrically, then the member is likely to bend or deflect. So the various, what are the various stages? First is your anchorage of tendon. Okay, it means tightening your tendon against the end abutments. Then there are placing of these jacks. These two side checks you can see here. Then there is application of the tension in the tendons. So we will pull these jacks and you will apply the tension into the tendon. Then there is a casting of concrete or the pouring of the concrete and cutting of the tendons. Once the tensioning is done, the pouring of concrete will be done. And after the hardening of concrete, we will just cut out the tendons. And when we will cut out the tendons, what will happen? The pre-stress will be transferred to the concrete with elastic shortening, and there may be formation of the camber. Camber is nothing but what will happen when we will cut the tendons from both the ends. So it will try to make a camber. Camber, let me show you how this one. Yes, when we will cut out the tendons from both the end, what will happen? Your wire will try to make a camber in the upward direction. Is it? And then it will be put into the service. Then an external load will nullify the effect of that compression into the concrete by giving the extra tensile force. This is the casting factory concrete mixer. Now, what are the advantages of the pre-stressing? Relative advantage over the post-tensioning. Okay, compared with the post-tensioning, can be pre-tensioning is suitable for precast member. Precast members are nothing but like slippers which are used in your railway lines. Okay, that is the pre-stress member and a pre-tension member. And in pre-tension, large anchorage devices are not required. Only you need the single bed. By using this only single bed, you can give pre-tensioning. You can apply pre-tensioning to the multiple members. There are few disadvantages of pre-stressing also, pre-tensioning also. This bed is required, pre-tensioning bed is required, and again there should be a waiting. Once these members will not get out of this bed, then and the concrete does not attain the sufficient strength, up to that you have to wait. Then next batch will come and pre-tensioning will be done. There should be again a good bond between concrete and steel over the transmission. Then there is post-tensioning. Okay, so what is post-tensioning? In post-tensioning, the tensioning in the strand or the tensioning of the wire is done after the concrete get hardens. Okay, in post tension the tendons are tensioned after the concrete has hardened. Commonly metal or plastic ducts are placed inside the concrete before its casting. After the concrete get hardens and get enough strength, the tendons was placed inside the duct and the strength inside the duct and stretch against the anchorages. Then there may be grout injection or not according to the bonded or unbonded tendons. In post-tensioning system, what happens? A duct or a tendon. Now see, pre-tensioning is a method which will be cast into the labs. Okay, it is a laboratory type of a tensioning. Okay, it will be done on the places where you are available with the beds, wherein your post tensioning is in situ type of tensioning. Okay, you have to apply tension on site only. It is not, it will be casted on the site, but a tensioning will be provided on the site where it has to be finally fixed or where it has to be finally used. So in post tensioning, the ducts for the tendon, ducts are, here you can see a vent pipe. This is nothing but your duct. Okay, a duct. For on inside this duct there will be tendon. There are number of tendons that are placed along the reinforcement before the casting of concrete. The tendons are placed in the duct after the casting of concrete. The duct prevent contact between concrete and the tendons during the tensioning operation. Unlike pre-tensioning, the tendons are pulled with the reaction acting against the hardened concrete. Here, once your concrete will get hardened, then the tensioning in the ducts will be done or will be given. If the ducts then will be filled with the grout, then it will be termed as your bonded post tension. And uh, if the grouting will not be done, then that this will be termed as your unbonded post tensioning. The grouting material may be your cement paste or sand cement mortar. So here for this operation what we need, first we need the casting of concrete. Okay, a concrete will be cast, then there will be placement of the tendons. Okay, the tendon will be placed, then there will be anchorage block on the both side. On both side you have to place the anchorage blocks. Then you have to apply the tension to the tendons. Okay, the tendons will be pulled from both the side by using the anchorages. Then there are wedges which will be applied after the, which will be there before the cutting of tendons, and once the wedges will be fixed, then there will be a cutting of tendon. Here you may see this assembly. Yes, just observe this figure. Here these are your tendons. Okay, this is nothing but your cavity. In this cavity, there will be a vent pipe or a pipe duct. Out of this duct, there will be passage of tendons. Okay, and this is nothing but your anchorage plate or an anchorage device. This plate is your anchorage device, and over here on this one tendon, there are small wedges which will fix those all tendons. In this figure, it is not actually clear. So to fix this single tendon, there is a there is small device called as wedges. Wedges should be placed over here though, so that your strand will be fixed into the anchorage plate. Okay. Once this assembly is get fixed over there, then there will be a stretching of tendon. And once you will stretch your tendon, that stretching or that force will be transferred to the concrete. Then there will be, we have to cut the extra amount of tendon, and this is nothing but your post tension. This is a precast segment girder or a post tension girder, but it is a precast, but a post tensioning will be done on side only. Okay. Then see, there are few advantages again of post tensioning over pre tensioning. First advantage can be post tensioning is basically suitable for the heavy cast in place members. Okay, which are cast in situ, which cannot be casted on site. So these are applicable for cast in situ members. Then waiting period for the casting is again quite less. Then transfer of pre-stress is independent of the transmission length, because here we have to stretch the tendon individually for the individual segment. Then disadvantage is the, it requires heavy equipments like grouting equipment, then anchorage devices, then wages. So these are extra accessories or the fixtures are necessary when we have to deal with the post tension. Okay, and what are various devices used for the post tensioning? Casting bed should be there, duct, anchoring devices, then jack to give the pulling force, then a jack machine, then there should be anchorages, wedges, then strands or tendons, and the grouting equipments. If you have to do the bonded tensioning, if not, then it is an option. Okay, we have seen the advantages and disadvantages. So now we will move to the analysis part. Okay, now when you are dealing with simple RCC beam, so how you will find out the stress of that RCC single beam? We have to find out the stress. Then we have to simply divide the load to the area. Is it? But when we are dealing with the pre-stress member, in that case, you are having two types of load. First one is your pre-stressing force, and another one is your external load. Is it? So first case, just consider a simple cross-sectional beam having a concentric load or concentric pre-stressing force. Here, in this C, you are applied a tendon is there, is it? So we have to pull the tendon from both the sides. So what is happening? You are applying a pulling force from both the sides. Okay, so this is a simple first condition. But first case is for the concentric tendon. Concentric means it is applied, a force will be applied to the center of the beam or the center of the section, center of the member. So for this case, your uniform pre-stress will be simple. Your applied load per unit area. Is it? That is load per unit area force by A, which is your compressive for the overall depth. So this is the case when you have to analyze the concentric pre-stress force. Now if suppose you have to apply a force with an eccentricity. Now in this case what will happen? First one will be your direct stress. Okay, that is the load because of the simple concentric force, that is P by A. Second force will be because of your eccentricity, and that will be your PE by Z. PE by Z is nothing but your moment by Z. Okay. Then your third force will be there because of the external load. Here you are applied with the UDL. So a load for the UDL will be there. Again there will be one more force, that is because of the dead load of UDL. So just observe this figure carefully and you will see that how analysis of pre-stress will be done. Now see, if you are given with the cross section, okay, if you are given with this beam, okay, but now here in this case you are given with the an external force, that is your UDL, plus you have to consider the self-weight of the beam. Okay, so two forces, two loads are there. First one is your external loading, okay, plus the dead load, plus third force is your pre-stressing force, okay, and fourth effect will be the pre-stressing force with the eccentricity. Okay, so how we will find out the total force in this? First one is your cross section. Okay, first your stress will be stress because of the direct force, that is your direct stress, that will be because of the pre-stressing force. How will you find out that? P divided by A. Okay, so this is your direct stress. Then second stress will be because of the eccentricity of that pre-stressing force. So that will be termed as your bending stress. Okay, because of that eccentric pre-stressing force. So that will be your M by Z, that is nothing but your PE by Z in tension and in compression. Bending stress will be negative on the upside and positive for the compressive side. Then third one will be your stress because of the dead load. Okay, excuse me. Whatever is the amount of dead load or the dead load intensity is given, applied load intensity is given, that will be your dead load stress. Okay, how will you find out dead load stress? Again, mg by zt. You have to find out mg moment because of that gravitational load. Okay, then third one is your, fourth one is your because of the dead load of this beam. Okay, so this is again m by z. So when you are having an externally applied beam or externally applied section with eccentric pre-stressing effect, in that case you have to consider four stresses. First one is because of the direct stress, second one is because of external eccentric external pre-stressing force, then third one is because of dead load, and fourth stress is because of the live load. So a resultant force or resultant stress will be the summation of all the stresses on the superior as well as on the inferior side. Okay, we will see one example that how to calculate these forces. Then there are two types of losses will be there. As it's supposed to be, you are applying an 1000 kilonewton of load on both the sides. Okay, you are applying a 1000 kilonewton of pre-stressing force to the beam. So what will happen? This 1000 kilonewton of load will not be transferred or will not stay constant during the lifespan of that structure or lifespan of that beam. What will happen? There will be losses because of the few reasons, and those losses are because of the either elastic shortening, friction, anchorage creep, shrinkage, or relaxation. So the basically pre-stress losses are classified into the two categories, that is your immediate pre-stressing losses and the time dependent pre-stressing losses. Immediate pre-stressing losses are your losses which are happened immediately after applying the pre-stressing force. So first pre-stressing force or pre-stressing loss is your elastic shortening. Elastic shortening is quantified by the drop in pre-stressing tendon due to the change in the strain in the tendon. Okay, if there will be change in the strain, if you are giving a total change in length of 5 mm, supposed to be, if you are pulling your tendon by 5 mm, uh, 5 mm of length of its length, then what will happen when you will cut the tendon? After its cutting, there will be either 10 to 15% regain of its size. So it will try to regain its length. So there will be maybe 0.5 mm or 0.6 mm of the regain into that strength. So that final strength which we have encountered will be only 4.5 mm. So that will be your elastic shortening or the immediate pre-stressing loss. Then another type of loss which can be happen is your frictional losses. Then there can be anchorage slip, and next are your time dependent losses. Time dependent losses are because of the creep and the relaxation of pre-stressing steel. Creep and shrinkage are nothing but what is creep? Creep is nothing but change in length without application of your external loading, or constant change in or increase in the length of the member without application of external loading. Is it? Then again there is a shrinkage in the concrete. Shrinkage is nothing but compression in the concrete, and relaxation of pre-stressing steel. That is nothing but the amount of tension or the amount of strain you have given to that strength that will try to regain its length over the period of time. That is nothing but a relaxation of pre-stressing steel. Okay, so these are the few types of losses which we have to consider. So in both the pre-tensioning and post-tensioning, uh, few losses are encountered in pre-tensioning and few losses we have to encounter in post-tensioning. Like in your elastic shortening, this we have to consider in pre-tensioning, but in post-tensioning, if as we have seen there are number of cables or number of tendons. So if we are tensioning all the tendons on the same time, then we do not have to consider the elastic shortening and post-tensioning. Perhaps if you are doing post-tensioning into the different stages on different days, then you have to consider the elastic shortening into the post tension. Okay, if wires are tension in single stage, then you do not have to consider the elastic shortening loss. Then anchorage slip in pre-tensioning, there is no anchorage slip. In post-tensioning, you have to consider. Again, frictional loss, it is not applicable in pre-tensioning because in pre-tensioning we have seen we have to use only a single bed. Is it? But in post-tensioning, there are number of types of devices in which there will be a frictional loss. Creep and shrinkage of concrete, this may be applicable for both pre-tensioning as well as for the post-tensioning, and relaxation of steel, again this will be applicable for both pre-tensioning and post-tensioning. When we have to find out the total amount of pre-stress, that what will be the amount of pre-stress, then it may range from 20 to 25% of the initial pre-stressing. That is, if supposed to be you have applied 1000 newton of the force or the 1000 newton of the pre-stress on both the sides, then there may be 20 to 25% loss into that pre-stress for post-tensioning and pre-tensioning respectively. In post-tensioning, it may vary up to 20,000 or 20%, and for pre-tensioning, it may vary up to the 25%. So, what will be the amount of pre-stress will left? Around 800 to 750 Newton. So just observe this figure. Consider the basic case of simply supported being subjected to your UDL. Okay. Now see, if you are considering a UDL, so in this case, what are the various forces we have to consider? First one is the direct stress. Second one is stress because of the eccentric tendon, then because of the external load. Here the dead here we do not know about the dead load of the beam, hence we will not consider it. If supposed to be you are given with the dead load, then again you have to consider them. Okay, so this will be your simple case. Here what are the different types of forces? First one is your force because of, or stress because of the direct loading or direct stress, and second because of the external loading. Okay, then here case 2, we have to consider the beam with the centroidal axis of the pre-stress. So for stress will be your direct stress P by A plus your stress because of the external load. Okay, so because of the external load, it will be P by Z. P by Z is nothing but your M by Z. Okay, first one will be because of the direct stress, and second is because of the external load. Here, because your tendon is placed centrally. Okay, this is your second case. So your total stress will be, first one is your because of direct stress, that is P by A. Then one more amount of stress will be there because of the external load, that is your MC by Z. So whatever will be the amount, you do not have to consider this equation or this formula. You can directly find out your stress by using or by adding these two ratios. Okay. Then consider the here we have considered your compression as positive and tension as negative. Then your third case, when your pre-stress is applied eccentrically. Okay. So if supposed to be your pre-stress is applied eccentrically, here how, what are the different types of loads you have to consider? You have to consider first pre-stress because of the uh, stress because of the pre-stressing force, that is your P by A, or a direct force or a direct stress. Okay. Second stress is stress because of the external loading, that is nothing but your uh, M by Z. Next, stress because of the pre-stressing force or eccentric pre-stressing force. This is nothing but a bending stress. So this will be Me by Z. Okay. So see in this figure here, first will be your simple direct stress, that is P by A. Second one will be because of the eccentricity, that is the bending stress P by Z, where negative sign represent your tension and positive side represent your compression. Third one is stress because of the external load, again MC by Z. Okay, so total stress on this beam will be a summation of all these stresses. That is P by A plus MC by Z minus P by Z for the superior side, and for the inferior side it will be P by A minus MC by Z plus P by Z. Okay, so there we have considered here three cases. First case, when you will consider a basic case of simply supported beam which is subjected to your UDL only. Okay, so when you are considering only UDL, no pre-stressing force is there, so your stress will be zero. Okay, for second case, when you had considered, when you were applying a pre-stressing force at the centroidal axis only. Okay, in that case, we are having two separate stresses. First one is for direct loading of pre-stress, and second one is because of the external loading. Okay, so it will be P by A plus MC by Z. And your third case is for when you are having eccentrically applied pre-stressing force, okay, with the external loading. Okay, so here your pre-stressing force will be summation of direct stress plus bending stress plus stress because of the imposed load. And if supposed to be you are given with the dead load again, so here it will be plus m by z for the dead load, and the configuration of the stress will be same as the live load. Okay, so we just consider also try to solve a simple example without considering an eccentricity. Okay, now here in this problem we do not have to consider eccentricity. It means you do not have to consider the bending effect. Okay, so what will be your total stress here? A direct stress, that is P by A, and stress because of the external loading if given. If not, then again we do not have to consider any sort of load. Okay, so what is given to us? Pre-stressing force is given. Okay, pulling force of 2500 kilonewton. Losses between transfer and serviceability. Okay, when pre-stressing has been done in stage 1 and when it is kept in serviceability. Serviceability, SLS is nothing but serviceability stage. Okay, so between transfer stage and serviceability stage, there is a loss of 20%. Then check the stresses, and we are given with the permissible stresses of FTT, FTS, FST and FPC. So this section is rectangular, 300 by 650 mm wide, and it is simply supported spanning 12 meter with dead load equal to self weight and a live load of 6 kilonewton meter. Okay, dead load is nothing but the self weight, so we have to find out the self weight. The pre-stressing force is applicable at the center. Okay, means eccentricity is not to be considered. Now section property is here, 300 by 650 mm deep beam is given to you. Okay, so find out the area, that is 300 by 650 mm. Then we have to find out the Z. So Z is nothing but the ratio of moment of inertia to the depth of your neutral axis. So here it is a rectangular beam, so it will be your depth of beam divided by 2, and moment of inertia for the rectangular beam is nothing but BD cube by 12. Okay, so it will be 300 into 650 cube by 12. So I is 6866 by into 10 to the power 6 mm to the power 4. And section modulus will be your I by x. So x is your h by 2. This is nothing but 325, and I is 6866 into 10 raised to power 6. Okay, so you will get your section modulus Z as 21.12 into 10 raised to power 6 mm cube. Again, here we know that BD cube by 12 divided by D cube by 2. This is nothing but here it is given H. So BH cube by 12 divided by H by 2. So it means your formula will reduce to BH cube by 6. Again, you will get the same answer for section modulus as 21.12 into 10 raised to the power 6 mm to the power 3. Okay. So this is for the compression side. Okay, and for the tension side, as it is a rectangular beam, it will be same with the negative sign. Okay, negative sign is for the bottom of the section, that is for the compression. Then the only applied loading and transfer will be self weight, which is density of concrete into area. We have to find out the self weight. So area into density, density of the PSC is 25 and area is 0.3 by 0.65. So you are getting 4.88 kilonewton per meter of self weight. Okay. So as it is a UDL, sorry, it is a simply supported beam. So we have to find out the maximum moment. So maximum moment for this will be WL square by 8. So this will comes out as 87.8 kilonewton meter. Okay. So total loading at the time of serviceability will be the imposed loading plus the dead load. So imposed load is nothing but your this load. self-weight that is 4.88 and a live load intensity is given as 6 kilonewton. So imposed load will be summation of both the loads, that is live load and the dead load or the self weight. So 4.88 is the self weight plus live load is 6. So its moment will be 195.8 kilonewton meter. Okay, so here first stress will be direct stress, that is P by A. Second stress will be stress because of the external loading. Okay, we will not consider or we do not have to consider the stress because of the eccentricity of the tendon, that is because of the bending. So final stress will be stress because of that axial loading, that is P by A, or the direct stress. So force, pre-stressing force is given to us as 2500 kilonewton. Okay, 2500 kilonewton into 10 raised to power 3 per newton divided by the area. Area is your 195,000 mm square. So we are getting 12.8 newton per mm square of stress or the direct stress. Okay, that is the 12.8. So this will be a uniform section of 12.8 on both the side, that is either on tension side and compression side. Then at transfer, the stress due to pre-stress applied and after the beam is lifted, the stress due to self-weight. The self-weight moment at the center generated a top stress of M by Z. Okay, the moment we had calculated as 87.8 divided by the Z, that is the section modulus. It is 21.12 into 10 to the power 6 mm cube. So just divide both the values, you will get 4.2 Newton per mm square. Now this is the weight at the time of or because of the pre-stress and after the beam is lifted. Okay, so this is the stress at the time of transfer. Hence the transfer check at the center will be, first one will be your load because of the pre-stress and because of the self-weight. You have to find out, here it is plus plus, then for the pre-stress we have seen the sign convention. Observe in this figure, this first one is for the direct stress, second this stress is because of the bending. Here eccentricity is not given, so we will not consider this bending. And third one is because of the dead load or live load. Okay, so your upper side or the compressive side is positive and tensile side is your negative. Okay, here you are not having the this stress, so you have to add this superior force and you have to subtract the inferior force. So here 12.8 plus 4.2 it is 70 and 12.8 minus 4.2 it will be going to give you 8.6. Okay, now at this serviceability, the pre-stress we are given with the 20% reduction between the transfer and serviceability. Is it? So at the uh, serviceability stage, the stress has reduced by 20%. The top and bottom stresses due to applied load will be the positive or negative 190.98.5, that into 10 to the power 6 divided by section modulus. That is nothing but your moment or serviceability moment. At the time of serviceability, what will happen? There will be total dead load plus live load. But at the time of transfer, there will be only a dead load. Okay, this understand this carefully. That is why you had calculated only, you had taken only the dead load or imposed load over here, a self weight here. But after serviceability or when your section is kept in service, in that case you have to deal with live load as well as the dead load. Is it? So for this case we had taken total moment because of the dead load and live load. This one 4.88. This is the dead load intensity plus 6. This is the live load intensity. Okay, so the total moment is 195.8 divided by section modulus. This is 21.12 into 10 raised to power 6. This will going to give us 9.3 positive negative Newton per mm square. Okay, so we have to add or subtract this from the pre-stress. Okay, so pre-stressing is your 12.8. So reduce your 12.8 20%, so it will going to become 10.2. Okay, and 9.3 stress because of the self weight or live load. You may calculate this individually also for dead load and for live load. You will get the same value. Okay, so 10.2 plus 9.5, here it will be 19.5, and pre-stress for the inferior side will be 10.2 minus 9.3, it will be a 0.9. Okay, there will be reduction into the pre-stress only. Okay, so we have reduced the pre-stressing or direct pre-stressing. That is, it is 12.8. So after reducing 20%, we are getting 10.2. Okay, so this will be your total amount of stress after the section kept into the service, or it is at the SLS stage, and these are your stresses at the transfer stage or at the time of transfer. So hopefully you have understood this problem, and just try to solve out more problems. You may refer Krishna Raju for this. This is the quite better book. It have full coverage of the of your RTM syllabus, along with your the competitive examination syllabus will also be covered into this book. In the book, more illustrative examples are given. So try to find out, and you have to apply the same theory at transfer and at serviceability. Once you will understand this figure, then you will be easily find out the stresses at various stages into the pre-stress. Okay, there may be also question to find out the to find out the different losses into the pre-stress. Okay, again they are having the formula based question. So just go with the equation, put the value, and you will get the different pre-stressing values or different pre-stressing losses because of the either in pre-tensioning or in post-tensioning.